section 7.2, part 2 for integration by parts. I got all the 2's in a row, right? So what's left for today is to talk about spicier examples. We covered earlier a few examples that were straightforward in terms of x times e to the x, right there in red. So x times e to the x, then x times sine x, and both of those work the same way. Then we saw that if we do x ln x, we have to switch things a little bit. And the moral of that story was that if you run into a brick wall, you turn around and run the other way, which means you make different picks for your u and dv. Obviously, dx part will always be a part of dv, because that's the portion where you integrate. But any function can end up being in u or dv part. The strange one was the ln x. Ln x, integral of ln x is not a basic integral, just like integral of tangent x is not, or integral of secant is not. So those are our basic, that look like basic functions, but they're not basic. We actually use integration by parts, and you can see over there how it's that done. We picked ln x to be the part that would differentiate, the u part, and then dv was dx, and we integrated and plugged in everything in the formula. I've been using this arrow, which shows the formula. It's u times v, which is where the arrow begins. And then we have v times du, where the arrow ends. So the arrow at the same time helps us with memorizing the formula for this very important and very frequent integration technique. So u substitution remains the most frequent, the most important technique. No matter what we learn now in chapter 7, u sub is going to be the one that you always try first, no matter what you learned in this section. And now that we got those basic examples out of the way, it's time for us to take a look at, let's say, something like this. Integral of x squared cosine x dx. So at this point, we are still going to try to get the function and the derivative. So we have u dv set up. And for u, we are going to pick x squared, and for dv part, cosine x dx. Now, I would like to talk a little bit about these choices before we actually continue working on the problem. The first thing that I want to bring here across is this idea that cosine cannot be removed by integration or differentiation, because it goes in that cycle of 4, right? Cosine, negative sine, then sine goes into cosine, then cosine into negative sine, and then negative sine into negative cosine, and so on. So there's a cycle of 4. So whether you differentiate or integrate that cosine, it will always remain in the mix, and it won't be removed. But x squared, on the other hand, will die in 2 iterations. If you differentiate x squared, you get x, and then you differentiate it one more time, you're at a constant level. So when you are picking these functions, you want to pick for u, if you can, a polynomial, because eventually, by taking derivatives, it will go away, leaving just the cosine or sine behind, or if you had e to the x or whatever else. So now, I'm going to go back to these examples that I did before and just see that at work. X times e to the x, I pick x to be u, because as soon as I differentiate it, I kill it, and look, the resulting integral has no polynomial term, because that differentiation killed it off. Absolutely same thing happens in the next example with the x sine x. If I pick sine, it would remain, the integral of x would be x squared, and I would just make it worse. You see that? I hope you see that. So if you make your choice and you make a wrong choice, you will see that the wrong choice will make the things in the integral worse, not better. This is better over here because you have no x. It's just cosine function. Well, minus minus give you plus, and then you go on. Now, that did not work here. We were not able to put x to be u because if you leave ln x for dv part, you don't know what integral of ln is because it's not a basic function. So we were forced to switch them and pick ln for u, put x in a dv part, and then even though the integration made it worse, the derivative of ln x was a polynomial here, and we lost that transcendental function behavior, transcendental function meaning into the x, ln x, sine and cosine and so on. So we lost that behavior, and the integral was again possible to be solved. So now, going back to our example, I have x squared cosine x, and the reason why I'm picking x squared to be u is because I don't want to make the problem worse. If I pick cosine for u, well, its derivative would be negative sine, and then the integral of x squared would be x cubed, and I just made everything worse. So I'm picking x squared for u, whose derivative is 2x dx. And then the integral of cosine is sine x. Awesome. Now we're going to put our arrow. And this becomes x squared sine x minus integral of 2x sine x dx. Did we achieve anything? The answer is yes. We did. It's better because it used to be x squared, now it's single x. Well, the bad news is that we have to do integration by parts one more time, right? To get rid of that x. But it was definitely better than the last time. So we're going to go u equals, you can do 2x if you want to. And then dv is sine x dx. Don't forget to write dx. It is very important. And then we have du as 2dx. And we have our function. What's the integral of sine?
Negative cosine.
Very good. Awesome. And now we put our arrow. Are you happy? All right. And so this blue integration by parts is for the integral. We have a non-integral term which we have to copy. Don't forget that one, okay? That's still a part of solution. So that x squared sine x needs to be copied, and then minus the rest, which is, I'll put everything in parentheses, minus 2x cosine x minus the integral of negative 2 cosine x dx. Way too many minus signs and parentheses, but we need them. Now we're going to get rid of them. X squared sine x minus and minus will give me plus 2x cosine x, and then minus and minus and minus will give me minus integral of 2 cosine x dx. So there was a triple minus sign over there. Integral of cosine is? Is it negative sine or sine? Sine. So 2x cosine x minus 2 sine x, and then we have plus c. Some of you know from exam it's either plus c or minus 1. You made those choices. And there it is. This is the answer. Now, if you differentiate this, it must go back into x squared cosine x. We have to get that as the answer. So that will be the check. You differentiate this answer, and if it works out, then it's correct. My question is, do I need to do that, or you got it for differentiation? Got it? All right. The second exam should be beautiful. The entire chapter on integration. You take your answer, you differentiate it, and you know whether it's right or wrong. Remember that part? And only thing that it's in a way is laziness. Exactly. Yep, I said it before. Thank you for paying attention. So this is the problem where you see that we used integration by parts twice because we had x squared. How many integration by parts for x to the 5 e to the x? 5, exactly. So that's something you can try once you go home on Sunday, have nothing to do. You crank up x to the 5 e to the x, see how it goes. What do you mean lunchtime? I said Sunday. Oh, you work Sundays? Ain't gonna fit in lunch break. Because you also have to eat.
Actually, I thought I'm actually getting this.
Hold that.
Oh, nice, real nice.
And now we're going to do integration by parts with limits. So you will compute the whole thing, and then you will apply limits at the end. So nothing special. Let's see, what would be the good problem to do? Maybe, well, let's try something cheaper, like
Call it an Android problem.
I'm sorry?
I said let's call it an Android problem.
No, I don't want an explosive problem. I want the cheaper problem.
Cheaper too.
So let's make it just annoying a little bit. So x sine 3x dx from 0 to pi over 2. So I put in the basic one-step integration by parts, so you can practice that. And when you get the solution, there's no plus c this time. It's going to be just computing the limits, good old way.
I know what the effective job is. He looks. It's fine. I'll wait for him. Right? Yeah. Just 109? I have no full talk report behind that. I have actually no. I got I over 6 minus 1. Yeah, the one. It's like, no. Oh, wait. And then negative integration of the negative and then get 3 x that's what you do. Like according to the equation. Yeah, this one is 0, but then if you put 0, it's going to give you -1. I mean 1, but it's going to be on the negative side. It's going to be cancelled out negative, so it's going to be positive. I haven't integrated it yet. Well, I mean, I integrated it. Yeah, that's good. I don't know, that's why I don't know. Right. It's still going to be negative 1. So it's like if you go over those if you pi over 2 negative pi, and then 3 pi over 2, it's going to be in this area.
Okay. I will casually work to 1/9. I've seen that 3 times. I would say -1/9 should be good, but just because I've seen it 3 times, because you're the third, so we'll see. U is equal to x. So I will just be solving this problem. You can follow along, or you can just do and finish your own thing, and then we'll see.
Can you scroll that down to that one signature D use? I don't have the same as mine. Okay, that I got.
Negative 1/9 is what I saw 3 students have, and now I have it as well, so I'm inclined to say it's good.
Is that saying the cosine becomes 0? What is the arrow with the 0?
Cosine goes through 0 at 3 pi over 2. Cosine is negative 1 at pi. 3 pi over 2 is 0, 2 pi is 1. Yes?
So you have the 2 negatives inside the integral and outside. So wouldn't that just make it positive?
But the integral of cosine is negative sign. No, integral of cosine is sine. Right? Yeah, I don't need this minus here. That changes this to plus.
Well, it should be a 3 pi over 2.
Yeah, which makes the sign
3
negative.
pi over 2, so it makes sign negative.
Because it's negative 1.
Oh, this is a 3 over here.
Right.
So the answer is negative 1.
Did you say the cosine is 0 at 3 pi over 2? That's what you said, right?
Cosine is 0 at 3 pi over 2. Sine is negative 1. Don't you know when you make 2 mistakes that cancel each other out into a right answer? Okay. Let's talk about a very interesting example. And that example says integral of e to the x times cosine x dx.
It's called the evil one for a reason.
So if you take a look at this one, what is the derivative of e to the x? And what is this 17th derivative of e to the x? And what's the integral of e to the x? And how about 30th integral of e to the x? Aha, so that one can't go away, either integral or derivative. How about the cosine? What's the derivative of cosine? Negative sine, right? And that's going to cycle forever no matter which derivative you ask about. How about the integral? Oh, so you catch the you catch my drift there, right? It doesn't really matter which one you pick where, because they're going to be awful anyway, right? So these are those evil problems where both of the functions are such that no matter whether you integrate or differentiate them, they never go away. And you just hope for the best as you start doing this that it's going to work somehow. There is an awesome way to solve these problems through complex variables, but we don't deal with that. Complex variables allow us to change this cosine into complex values, and if I give those lectures, I will let you know if you're interested to see that stuff. But in this case, since we want to deal only with the real domain mathematics, it becomes tricky. So we'll have to persist through this, and I'm just going to try and see how this goes. So I'm going to go say u equals e to the x, and dv equals cosine x dx, and then hope for the best, right? So du is e to the x dx, and v would be integral of cosine, which is just sine x. And we're going to put our arrow that helps with the formula. So this whole thing becomes e to the x sine x minus the integral of e to the x sine x dx. And it looks like we haven't achieved much, right? So I'm in awe of the person that did this for the first time. Because what's the definition of insanity?
Doing the same thing.
Yeah, doing the same thing over and over again, hoping for a different outcome, right? Well, someone at some point said, we achieved nothing. Let's do it again. So let's do one more integration by parts. And u equal e to the x, and this time dv is sine x dx. And when we go with the du part, it's e to the x dx, and v is going to be integral of sine, which is negative cosine x. And we put our red arrow again, which helps with formula. Don't forget to copy the first term, which is e to the x sine x. And then we have minus, and in parentheses we have the new stuff, which is negative e to the x cosine x, minus, and minus will give me plus the integral of e to the x cosine x dx. Get rid of the algebra there, parentheses. It's going to be plus e to the x cosine x minus the integral of e to the x cosine x dx. And what do we see here? Which is the same as where we started from, right? So we came right back where we started. Exactly. That's exactly what we are going to do. Very good. So now if you look at this, this is one continuous stream over here, right? Equal, 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 equal. So that means that I can take this and bring it to the other side of the equal sign, technically add this to both sides. It would add to this, because this is what's in the other side of the equal sign. So once I do that, I will get two integrals of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x. Because that's all that remains once the integral goes to the left. It's a trick, which is awesome. And now just divide both sides by 2. So integral of e to the x cosine x dx, which is what we were trying to compute, is equal to 1/2, and you can factor e to the x and get just sine x plus cosine x. and then plus c, or minus 1, whatever you like.
I mean, -1 is a
Yes, every time there is no plus c, there is a constant -1 per problem.
Question.
I think this was awesome.
So that's the end result, is two equations set next to each other.
Well, this was the question, right? That was the question,
Oh, I see what you're saying.
and that's the answer on the other end. Except it's a little bit unorthodox how we got it. So I will explain this one more time. Put 6 of these on the exam, right? Just kidding. So we start with the integral, and we do integration by parts twice, and we end up with the line on the bottom. So you should have no issues between the first and the last line. That is all standard stuff we learned last class. You are doing integration by parts twice. You must know the formula. So all of that stuff needs to be there. Once you are at the last line, this is where you realize that the part of this line is the exactly same integral as the one you started with. This integral is here, right here, because this is equal to this, equal to this, equal to this, so you just get rid of these 2 lines. So that's the same. We are literally moving, just like when you subtract 3 on both sides in the equation, you're subtracting, right? You add this one to the other side, which is one of those. 1 apple plus 1 apple is 2 apples, which is the next line. So 2 of those integrals that you want to solve are equal to this, which means that one of those integrals, when you divide by 2, will be this side divided by 2, which is when 1/2 comes from. You only have 2 flavors of this problem. You can have e to the x sine x or e to the x cosine x. And then if I need to make it annoying, it's going to be e to the minus x, e to the minus 5x, sine 3x, stuff like that. But that's just to introduce those annoying constants that you can drag around. But the process of the problem is absolutely the same. You just have to be focused on not messing up those constants. And that would be the evil problem. So just want to make sure and see if everything is covered. Which is great. The website exploded, which means I can't get to the book. That's okay. So this is integration by parts. You must memorize the formula. I already told you that the integration by parts is backwards product rule. So it is a very important technique. Later on, if you continue your graduate level mathematics, you guys will see these problems see this technique used as a technique to work some of the proofs in a graduate level math. That ends 7.2. Now, preparation for 7.3 and 7.4. Great. I know. It's going to be epic. So next class, which is on Wednesday, we're just going to be briefly talking about the trig review. Next class, we will have the full lecture on 7.3 and if time permits, 7.4. So we'll see how that goes.